Okay. Good morning, students. Till now, we have learned about the different wireframe modeling techniques and surface modeling techniques regarding solid modeling. Now, and also I have given a brief description about the solid modeling techniques. Okay. Now we can move into depth about the solid modeling techniques and their different types and their characteristics, the procedure of modeling different objects using these solid modeling techniques. You can now deal. Okay, right. So for this one, the first one is how to create the models by using different techniques. That we can learn now. Okay. So creating objects using. Okay, now in this one, the first one is that is what is called boundary representation method. Okay, boundary representation method. By using this one, we can model the different solid elements. At the same time, second one is CSG model. CSG modeling technique. C means constructive, S means solid, G means geometry. Constructive solid geometry modeling for constructing the different solid models in computer graphics or by using CAD softwares. Okay, right. So, Kiran, okay. Set theory. You know the set theory in the 10th class standard. Okay, right. So, set theory operations also you know. One is A union B, first one. Second one is A minus B, and difference, that is called. And third one is A intersection B. A intersection B is common points we will get from A and B. Now, how we are using this set theory for modeling the solid components? Okay, so you know that every solid component contains a assemblage of all the points. It contains so many points on the model. Okay, any object, any geometrical object, okay, is formed from the points only. Okay, suppose we want to model a rectangular plane. First we have to take a point, and also you have to generate a straight line from that point. Then you have to sweep that straight line along a fixed direction to get the rectangle. That means any component will be start from the point. Okay, any geometrical component will start from the point. Right. So here A means in this set theory, A means A component, A solid 3D component, and B means B 3D component, and so 3D components. Okay, now we have to apply A union B. What is A union B? A union B will give the common points belonging to A and B. Not only common points, all the points belonging to either A and B. That means A or B, any points. Suppose you want to assemble two components A and B. Okay, some points are there on A, some points are belonging to the B. If you take the points, those are belonging to the either A or B, those points are called A and B. Suppose if you go for the difference operation, that means B minus A. So from B we are eliminating the points belonging to the A component. Similarly, A intersection B. In A intersection B, common points belonging to the both A and B. That means those points have to present within the A or within the B. So, like this, we will apply the set theory for evaluating the different Boolean operations. These union, difference, and intersection are called Boolean operations. Now, for these Boolean operations, we will evaluate. We will apply union by using these Boolean operations. We will get the different components. Okay, from a set of individual components. Right. Now we can go for the next slide. There we can observe the examples belonging to the assemblage of different components. Okay. Right. Okay. Right. Here for union operation and for Boolean difference operation and for intersection operations, here I have considered two components. One is A and B. A is rectangular block, B is cylinder. And now I want to in this slide I want to get A union B. The diagram also showing on the screen. A union B, right side of the green arrow, you will get the A union B. And also below A and B, no, you will have the red colored and blue colored sphere. There is sphere is there. Okay. Anyway, those that is the 3D representation of assembling of A and B. Okay, right. So in A union B, yeah, as I have told in the previous slide, union operation will be performed on the coordinates belonging to the component A and component B. You can go for the next slide. In this slide, A minus B we are getting. So I know you know that A minus B means all the points belonging to the A, but not in B. But not in B. That will be appeared on the diagram. Okay, difference operation. Similarly, now we can go for the next example, A intersection B. Here in this slide, A intersection B, the points common to the A component and B component are presented there, and the resulting object also as shown in the figure there. Okay, you can easily observe those things also. Now another example he has given. That is a small rectangular plate at the same time large cylindrical component. Okay, A component and B component. A is the small rectangular component. That means thickness is less. A thin rectangular component like that we are called. Then he has given yes, a cylindrical object. So A and B, the diagram, 3D diagram below the given above drawn A and AB diagram from AutoCAD, that will be represented there, 3D diagram. Okay, right, that will give the A and B. Next slide, we can move on to the next slide. In this one, A intersection A minus B, that is also B minus A, both are on the right side. Okay, right side, we can observe those things. A minus B and B minus A, both are, you can observe there. Next one is the A intersection B also, we can observe there. Okay, right. Next, these equations are not required at this moment. We can go for the equations from after completion of the basic theory. Okay, right. Okay, now again we have to recollect the concept belonging to the geometry and the topology. What is the geometry? Geometry of an object. So for modeling any 3D component, we require both geometry and the topology. First go for the geometry. Geometry will give the length of the object and also the angle between the different objects, angle of inclination, or next one is suppose if you take a circle, center of the circle and diameter of the circle we require. So like that, geometrical data contains the dimensions and position of the object. Okay, after that one there is another terminology there, that is topology for assembling the different objects. Topology means connectivity and associativity of different components, that we have to specify in topology. Okay, right. Right. In topology, as we are seeing in the slide, okay, I already told you connectivity and associated. For that one, different examples also he has given. Those examples you can see now. This is one example. These are one example for showing difference between geometry and topology. Go for the first top left corner diagram. In the diagram, and right diagram also, both, if you compare both the diagrams, their geometry is same. But topology is different. How we can say geometry is same? In the left side diagram, top left diagram, if you consider L1, L2, L3 are the three lines. At the same time, L4 is radius of arc. R is there, radius of arc. L4 is there. Next L6, L5 are also there. Okay. Now next, if you go for the right side diagram, okay, the L5 and L6 are inner side. In the left side diagram, L5 and L6 are outer side. That means same size of element, geometric elements, they are joined each other with different ways, two different ways. In one way, L5 and L6 are L6 are in outside, and in another way, L5 and L6 are inner side. And next, go for the bottom left corner diagram. In that one, L1, L2, L3, L4 are, and like that we have the same diagram. But what about right side also same, right side, but right side geometry is different for left side and right side. Connectivity is same. How we can say that one? In the left side diagram, bottom left side diagram, L1, L2, L3, all these L1, L2, L1 is common for both L2 and L3 are reduced. Their lines lengths are reduced. L4 length also reduced. But in the right side diagram, L2 and L3 are reduced, already I told you, but L5, L6 are enlarged. That means geometry dimensions has been changed. Dimension changed, topology, connectivity is similar. Hence, here for this border diagram, okay, we can say that same topology but different geometry. That means same connectivity same, but dimensions are different, and accessibility also same. So by observing these diagrams, we can easily understand what is topology and what is geometry, right? Next, we can go for another example. In this example, if you observe this one, planar already considered 3 lines L1, L2, L3, circular arc C1. Okay, and the first 3 lines L1, L2, L3 and arc C1 are connected as the circular arc is inside the 3 lines, and on right side same geometrical elements L1, L2, L3 with the same dimensions, circular arc C1 also same dimension. That circular arc will be has been connected as that arc will be outside of the 3 lines. So dimensions are same, elements are same, but they are different. Hence, it is called same geometry with a different topology. Suppose you go for the bottom diagram, there again same elements L1, L2, L3, circular arc C1. Right side also L1, L2, L3, circular arc C1. But here they have been, there is L1 and L2 and L3 and L1. Geometry, angle is changed. Angle has been changed. At the same time, the position of the center of the circular arc C1 also has been changed. Hence, here the geometries are same. L1, L2 same length, L3 same length, C1 same length, but their angles are different. That means, but angle is different. The angle is nothing but a dimension. Hence, same topology, connectivity is similar, but geometry is different. So, by using all these examples, we can say that we can understand that what is the difference between topology and geometry. So, for modeling any component, these topology and geometric component concept is required. How they, suppose if you have same sizes components, how they are connected to each other, that is important. That is topology. If different size dimensional components required, how they are connected, that is also required here. Hence, they divided this connectivity, associativity, geometric dimensions into geometry and topology, right? So these concepts they have been introduced for this purpose. Okay. At this moment, now I will come. We can get into the primitives. We can get into the real solid modeling technique, that is constructive solid geometric technique, and also boundary representation technique. These two the constructive solid geometry technique. In this technique, okay, we will consider the different solid models, basic solid models. Now, all these solid models you can observe on the screen. First one is cone, second one is below that one is rectangular block, below that one is cylindrical block, right side is wedge, in between sphere and wedge there is a torus. Okay, right. Next one is CSG. What is the main concept we use for modeling different components using constructive solid geometry? The main process is from the primitives we will apply Boolean operations. That's it. Simply Boolean operations we will apply for modern different components using constructive solid geometric techniques. Okay. So primitives. What are primitives? I already told you. Basic geometric objects. 3D objects or 2D or anything. Here, majorly we will consider 3D objects as the primitives. The first one is cycloid, second one is cylinder, next one is prisms. All these things, pyramids, spheres and cones, all these are primitive objects. These diagrams have been shown in the screen in the previous class. Okay, right. What it will indicate? Constructive geometry, what it will indicate? It indicates the properties of different solids. Okay, right. Next slide. Here is an example for modeling a component as shown in the slide. Here is an example for modeling a component as shown in the slide by using constructive solid geometry technique. Okay. So before that one also I have explained how to get the set theory, how to get a rectangular A union B for a rectangular component and cylindrical component, A union B, A intersection B, A minus B, all these things we got in the in the set theory. So here is a different component. Okay, right. That isometric view of the component is shown within the figure. How it will be appeared, we can see in the next slide. Here you can first we have to model the. If you observe the entire component, there is one rectangular block and one cylindrical component. Both are shown on the right side. First, what he has done, A union B he did it. Okay, that means he placed the cylinder over the rectangular block. Right. And then, okay, next. Next, what he did? A union B minus B. A union B minus another component is there, that maybe C. Okay, from what is called cylinder. From cylinder to get the hollow cylinder, solid cylinder to hollow cylinder, he did the minus operation. Okay, from the A union B with another component called C. That C is subtracted from B cylindrical solid cylindrical component. Okay. Okay. Hence, we will get this component as shown in below by using constructive solid geometry. Again, the required component is not obtained. We require another component and another operation. Right. Now, he consider another smaller rectangular block, and that will be subtracted from the previous obtained block or object. Okay. So here again I am explaining. First, immediately what we required a rectangular block and a solid cylinder. First, union is applied. That means A union B. Next, you consider another small diameter. That is required diameter, smaller required diameter cylinder, and that will be subtracted from the B component, that is solid cylinder. And next one we consider another smaller rectangular block, which is compared with the second rectangular block. What we have shown in the what is called slide. By subtracting the smaller rectangular block from that obtained diagram, we will get the final component. So by using Boolean operations like union, intersection, and difference, only we will get this constructive this final required component. Okay, using constructive solid geometry technique. Okay, this is the example for how the Boolean operations are applied for getting the required solid component using constructive solid geometry technique. Okay, right. So. And all these operations are shown by using a binary tree. All these operations are shown by using a binary tree as shown in the diagram. Okay, right. So in this binary tree, first he has considered one diagram. Okay, first we have one geometry. From there, from top to bottom or bottom to top, we can move. Okay, top down approach or bottom up approach is anyway. Bottom to top approach we have to take intersection minus and union, and top to bottom minus intersection and union, like that we have to take by using this slide. Okay, right. What are the advantages of constructive solid geometry? Okay, so now using constructive solid geometry, the following advantages are there. One is it is a powerful and high level commands are there we present in the software. By using this one, we can save the time. We can now directly get the objects. And also there is a disadvantage for this one. The main disadvantage is it requires more computational requirement. That means calculations require more. For that one, we require high-end computers. Okay, right. That is the major disadvantage. And advantages, so many things are there. Easy to construct a solid model. Minimum number of steps we required only. And also modeling technique lead to concise database. Database is very concise, but as I told you, calculation power it requires more speed to high-end computers for the case of calculations. Okay, right. Those things they are displayed on the screen. You can know from that screen. Okay, this is the concept behind the constructive solid geometry for modeling different components. Okay, from the primitives, basic geometrical components. Okay. Thank you very much for all of you. I will continue the boundary representation method for constructing the different solids in the next class. Thank you very much for all.